In this video, we do basically the same thing that we did in the last video. We're given a function involving a logarithm, and we want to sketch the graph. So we want to use all of the tools that we've learned throughout the Calculus 1 course. We learned about limits. We learned about asymptotes. We learned about, we reviewed a little bit about the domain of functions of a real variable. We also learned the first derivative test and second derivative test and how to interpret the sign of f prime and f double prime. So we know all of those things, and we want to put all of those pieces together to just graph this function. And the goal is to be able to graph this by hand if possible without using the graphing calculator. But I always like to confirm that my graph is what it's supposed to be by using the graphing calculator. So we're going to start not by graphing this function, but by thinking about the domain, and then we're going to try to graph it on paper, and then we're going to check our work against the graphs online. So first we'll find the domain of f. We want to know which x values we're are allowed to plug into this function. So the implied domain is a set of all x values, all real x values, such that, well, what's inside the logarithm is positive. So x squared divided by 16 has to be positive. You would also want to make sure that you're not taking the square root or the fourth root or any kind of even root of a negative number, but there are no even roots in this. We also want to make sure we're not dividing by 0. We don't have any division involving any functions of x. We're dividing by 16, but that's never 0. And then, of course, the other thing that we always worry about is we want to take the log of a positive number, because you can't take the logarithm of 0 and you can't take the log of a negative number in the real number system. So we know that that's true. So we need x squared over 16 to be positive, which means that x squared is positive. And we know that x squared just looks like this, right? X squared is almost always positive, except for when it's 0. So we're going to have a problem when x equals 0 here. So the domain is all real numbers except x equals 0. So that domain is actually negative infinity to 0, union 0 to infinity. Now we could rewrite this if we wanted to. When I see that x squared divided by 16, the first thing that comes to mind is that that is actually natural log of x over 4 quantity squared. With that in mind, I can use this log property that the log of a to the n is n times log of a. So I can bring that 2 out front. We have 2 times x squared times this x divided by 4. But we have to be careful because this function has a domain of 0 to infinity, and this function has a domain of all real numbers except for 0. So we need to make sure that our x values that are negative are still in the domain of this function. So we'll just put absolute value bars on this. Because if I bring this 2 inside, if I take the absolute value of x over 4 and square it, I get x squared divided by 16, which is the same thing that I get if I take x over 4 and square it. I get x over 16. Now the absolute value bars around the x and the 4, or that x over 4, now this function is well defined on negative infinity to 0 as well as 0 to infinity. So this function is truly equal to this function. And I've simplified the inside function by factoring out that 2, or not factoring it out, but bringing that 2 out front using that log property. So this is our f of x. And if we want to, we can even simplify that further. This is 2x squared times the natural log of the absolute value of 1/4, that's our constant, times x. And I like writing it like that because it makes it easier when we take the derivative. So dividing by 4 is the same as multiplying by 1/4. So now I've got a constant times x, and take the derivative, I'm just going to get the constant, right? Okay, so this is our f of x. We've simplified it as much as possible. Okay. And now that we have simplified f and we know the domain of f, we'd like to find any critical points of f. Now, finding critical points involves computing f prime and then setting that derivative equal to 0 and solving for x. Now, f prime requires, or computing f prime requires a product rule. We've got a first function here and a second function here. The derivative of a product is the derivative of the first. So that's 2 times the derivative of x squared. So 2 times 2x, which is 4x, times the second, undifferentiated, plus the derivative of the second. Now, the derivative of the second function requires the chain rule because we have natural log of the absolute value of x there, or natural log of the absolute value of a function of x. So its derivative is 1 divided by that inside function. Actually, you don't need the absolute value bars. Times the derivative of the inside by the chain rule. And the derivative of 1/4 x is just 1/4. So this is 4x times natural log of the absolute value of 1/4 x plus 1 over 4 times x times 1 divided by 4. And if we multiply that 1/4 and the 4 together, we just get a 1. So this is a 1 over x times this, or plus this 4x times the natural log of 1/4 x, or the absolute value of 1/4 x. So that's our f prime. If we want to, we can get a common denominator. We can multiply this by x divided by x. If I multiply the numerator by x, I'm going to have an x squared. If I multiply the denominator by x, I just get an x in that denominator. Then we can add the numerators. So we have 4x squared times natural log of the absolute value of 1/4 x plus 1, all divided by x. That's our f prime. So we computed f prime, then we simplified. So I wrote it as a single fraction. It makes it a little bit easier to determine when the derivative is equal to 0. Actually, it's not as easy this time. We've got this polynomial times a natural log function, right? It's a little bit tricky. Say, okay, well, f prime, let's see when it's undefined now. We'll say it's undefined when x equals 0, because this is a 0 times negative infinity in determinant form as x approaches 0, divided by 0. So I've got an indeterminate form plus 1 in the numerator, divided by 0 in the denominator. So when x equals 0, our f prime is undefined. Now x equals 0, is that in the domain? No, it's not in the domain. So x equals 0 is not a critical point, but it is going to be a number on our number line when we draw our sign chart for f prime. We're going to determine those intervals. And f prime of x equals 0 when the numerator is 0. I'm actually not sure when that numerator is 0. So you might say, okay, well, when does that happen? Well, we could subtract 1 from both sides. And then divide both sides by 4x squared, and I would have this. A natural log equals this. Now, I don't know very much about what 4x squared times the natural log of 1/4 x plus 1 looks like. But I know what natural log of x looks like, and I know what negative 1/4 or negative 1 divided by 4x squared looks like. Because I know what those two graphs look like, I can infer basically how many points of intersection those two graphs would have. The x coordinates of the points of intersection of the graphs of y sub 1 of x, where this is our first function, and y sub 2 of x, where this is our second function. The x coordinates where those two y values are the same are the solutions to this equation. So let's look at y sub 1 of x. It's just a logarithm, but dividing all of those x values by 4 actually stretches it horizontally in the x direction. Without any tick marks on the x-axis, though, it's just going to look like any other logarithm. When x equals 1, we're going to have log of 1, which is, or when x equals not 1 in this case. When x equals 4, we'll have 1/4 times 4, which is 1. So we'll have the log of 1, which would be 0. So that intercept is at x equals 4. And otherwise, the function looks the same as that logarithmic function. And now because we have the absolute value there, we're gonna have the same thing on the other side when x is negative. There should be some symmetry. And when x is -4, we'd have 1/4 times -4, which is -1. The absolute value of -1 is +1. Natural log of +1 is 0. So that's what this function looks like. And 1 divided by x squared looks like this. It looks like 1 over x, but then we square it, so all the y values on the graph become positive. But then if you multiply by 4 and then a -1, the y values on the graph would be negative instead of positive. We can tell that this is always negative, right? So I'm gonna have a graph that looks roughly like this. Say, okay, I don't actually know when those two functions cross, but I imagine that they probably do. This function and this function cross this function and this function somewhere, I imagine. I just don't know what it looks like. So I think that we might have 2 points of intersection, and they're probably small x values. So I think I'll graph this on Desmos in order to infer what those x coordinates are. And once we find those will be the x values and our sign chart for f prime. So we're gonna have f prime. We're gonna make a sign chart and have 0 as it's not a critical number, but it's one of the x values on the chart. And then we should have, I think, 2 x values here when these curves cross, but that's just a guess. I need to figure out when this function is equal to this function. And then we'll look at the sign of these factors on each of those intervals. And then the sign of x, that's in the denominator. X is negative on each of these intervals and positive on each of these. So then once we find that, we need to, or once we find the x values where those two graphs cross, we need to infer the sign of this expression on each of these intervals. So f prime will be this divided by that. Okay, I was going to try to do everything by hand, but this particular function is pretty complicated. So I want to actually look at the graphs of natural log of 1/4 x, or an absolute value of 1/4 x, and the -1 over 4x squared, and see where those graphs cross on Desmos.com. Okay, so this is our function y. Looks roughly like that. And I think I should call it f of x so that it has a better name. And then we said if we wanted to, this is x squared divided by 4 squared, so we can bring a 2 out front and just call this the absolute value of x divided by 4 instead. And then we see it's the same graph. And we said, okay, what is f prime? We did a bunch of calculations and we got 4x squared times natural log, well, times the same logarithm that we have right there. I'm just going to copy and paste that. Plus 1. We want all of that divided by x. So that's what the second derivative looks like. Or sorry, first derivative looks like. And we can see that first derivative actually has several 0 points. And the first derivative is 0 at a -3.94 approximately and positive 3.94. And then it's also equal to 0 at a negative 0.32 and positive 0.32. You might say, how do you know that? Well, it's whenever that natural log of 1/4 x, or the natural log of the absolute value of 1/4 x, is equal to that -1 divided by 4x squared. So if we take this numerator and and we say, when is that numerator equal to 0? We could graph it, or we could just graph, let's say y1 is natural log of the absolute value of x divided by 4. And y sub 2 is that -1 divided by 4x squared. And that numerator of f prime is equal to 0 at the points of intersection of those two curves. So we actually have 4 points of intersection. And we have a lot of symmetry. So it looks like they intersect at, looks like -4, 0. That's not right. When x equals -4, this natural log function is 0. But if x equals -4 here, we'd have -1 divided by 64. So that's not what we want. But it looks like that x equals -3.93597 is our first x coordinate where y1 and y2 meet. So f prime, I think it's going to be 0 at -3.93597. It's not exactly 0, but it's really close. And then by symmetry, we should have the same thing on the other side over here. I think those intersect at exactly the same x value, but positive. And we see that that y value on f prime is very, very small. Now I said that there's also another x value where they intersect. It looks like that -0.3133. And that is that y value is nearly 0 on the derivative graph. And we see the same thing on the other side for symmetry. So f prime is equal to 0 actually at 4 different values approximately. It's where those curves meet. And we can put all of that together on our number line. I thought we'd only have 4 intervals, but it looks like we're going to have 6 intervals. Make another number line over here. So we had that -3.94 approximately and +3.94. And then we had -0.31 and +0.31. And then we had that 0 where the original function was undefined. So we have to look at the sign of f prime on this interval, this interval, this interval, this interval, this interval, and this interval. And that's relatively easy to do. F prime is 4x squared times natural log of the absolute value of x divided by 4 plus 1, all divided by x. So x is negative on these 3 intervals, and x is positive on these 3 intervals. And then this we can infer by looking at the relationship between y1 and y2, that f prime will be positive, or excuse me, this factor will be positive when natural log of the absolute value of x divided by 4 is greater than -1 divided by 4x squared. So that is when y sub 1 of x is greater than y sub 2 of x. We're just going to look for when the intervals where those function values on the log graph are greater than the function values on the negative 1/4 negative 1 divided by 4x squared graph. Okay, so when are the y values on the orange graph above the y values on this other graph? So get this out of the way for a second. We say, well, the y values on the orange graph are above the pink values on, or the graph, or the y values on the pink graph. When we go past this point, that negative 3.94 approximately. So from negative infinity to that negative 3.94, we have this number minus this number, or excuse me, or this function is greater than this function. And that when the orange function is above the pink function, that means our numerator is positive. So our numerator is positive on the interval from negative infinity to negative 3.94. And then on the next interval, the pink function is above the orange function. So things have flipped. So that means our sign's going to be negative. They have these values minus those or these y values minus those. And then that will be negative. And then from this x value of negative 0.31 to 0, the orange values are larger. So this y value minus this y value is going to be positive there. And then the same thing happens from 0 to the positive 0.31. And then from that 0.31 to that positive 3.94, the pink values are above the orange values. So when the pink values are above the orange values, the difference is negative. And then when the orange values are larger than the pink values, we get a positive answer again. Okay, so that should allow us to complete our sign chart. So f prime is this positive divided by a negative on this interval, so that's going to be a negative. We have a negative divided by a negative, which is positive, then a positive divided by a negative, which is negative, a positive divided by a positive, which is positive, a negative divided by a positive, which is negative, and then a positive divided by a positive, which is positive. So our function goes from decreasing to having a 0 slope to increasing, and then it goes from increasing to having a 0 slope to decreasing. And x equals 0 is not in the domain, so we skip that one. And then it goes from increasing to having a 0 slope to decreasing. And then it goes from decreasing to having a 0 slope to increasing. So it looks like we've got a relative min at negative 3.94 and positive 3.94, and a relative max at this negative 0.31 and positive 0.31. Just by the first derivative test. And then at x equals 0, I'm really not sure what we have. We've got, well, the natural law, we've got a 0 times negative infinity in determinant form as x approaches 0. So we'd have to evaluate that limit as x approaches 0 to infer the behavior of the graph near 0. But we've got, because of the sign changes in f prime, due to the first derivative test, we can infer that these x values correspond to relative minima, and these x values correspond to relative maxima. So let's go to Desmos and graph those, or at least plot those points. So I claimed that I had a relative min at this negative 3.94 and the positive 3.94. So let's evaluate the function there. Oh, we already did, right? Oh, no, we evaluated the derivative at those values. So rather than evaluating the derivative at those values, let's evaluate the function there. So I have negative 3.93597. And I don't want the derivative, but the function itself. Looks like I must have made a mistake. Because my sign chart indicated that the sign of f prime changed at negative 3.94, and I don't see that. The sign, it looks like the function, the derivative is supposed to be negative there. And then the same thing is true at the other side. The derivative should be positive there. I wonder what happened. Okay. And then we also had this other x value. Looks like the minimum occurs at x equals negative 2.46. I've got a negative 0.3133. Okay, so that doesn't look like we've got a derivative of 0 there. Okay, so I think I must have made a differentiation error. That must be it. Because this function actually does, or this numerator does change signs at those 4 x values. But it looks like from this graph that I've got a relative minimum here at approximately negative 2.42. And another one at positive 2.42. Looks like I've got a relative max at 0, right? Oh, looks like we've got an undefined point there. So the limit as x approaches 0 is 0. But the function value doesn't exist there. So this derivative must be wrong. Let's go back to our pencil and paper calculations and see if we can't compute that derivative again. When I computed the derivative of this, I used the product rule. I said the derivative of the first times the second plus the derivative of the second. So that's 1 divided by the inside function times the derivative of the inside times the first. I forgot to multiply by the first. Do. Well, that'll do it. So if we divide by, or if we multiply by that 2x squared here, we end up with a 2x squared divided by x. So one of those x's will reduce. And this ends up being a 2x term. So all of this is incorrect because our derivative was calculated incorrectly. All right. So I don't need to get a common denominator because there is no denominator. F prime is 4x times natural log of 1/4 x in absolute value plus 2x. Let's write that down on the next page, make it look a little neater, and then we'll factor it. Then I think we'll find the right x values this time. Can't believe I forgot to multiply by the other function, but I don't think I've ever done that before. I've often thought, don't forget to do that when I was thinking through the exercise of computing these derivatives, but I've never actually done that myself. First time for everything though. So f prime is 4x times the natural log of the absolute value of 1/4 x plus 2x. We see that these terms have a 2x in common, so you can factor that out. You say 2x times 2 times the natural log of the absolute value of 1/4 x gives us our first term, and 2x times a positive 1 gives us our second term. This looks much better, given what that graph looks like. So f prime is going to be 0 when the first factor is 0, or the second factor is 0. So from this equation, we have x equals 0 is when f prime equals 0. And then from this equation, we have natural log of the absolute value of x divided by 4 equals, subtract 1 from both sides, divide by 2, negative 1/2. And then to get rid of the log, we exponentiate. So we have the absolute value of x divided by 4 is 1 divided by square root of e. And then multiply both sides by 4. to get that absolute value or to get the absolute value of x by itself. And then if if the absolute value of x is 4 divided by the square root of e, then x must be plus or minus 4 divided by the square root of e. Okay, now that's looking a lot better. That's looking a lot more like our graph. Now, if we evaluate f at 0, well, actually, we can't evaluate f at 0, right? Because the log of 0 is undefined. So I can't do that. But we can take the limit as x approaches 0, and we'll do that in a moment. And then we can also substitute x equals plus or minus 4 divided by the square root of e. So f is 2x squared times natural log of the absolute value of our input value. So we're going to input plus or minus 4 divided by the square root of e. Square the numerator, you get 16. Square the denominator, you get e. The absolute value of this is just going to give us a 4 divided by square root of e, or you can call that e to the 1/2 if you prefer. So I end up with 32 divided by e. And then I have natural log of a quotient. We've got that log property that allows us to simplify. Log of a quotient, whoops, you guys can't see that. There we go. Is log of the numerator minus log of the denominator. So this expression is actually log of 4 minus log of e to the 1/2. And log of e to the 1/2 answers a question. It says e to what power is e to the 1/2? So this is just going to be a 1/2. So we end up with 32 over e times natural log of 4 minus 1/2. And if we wanted to, well, actually, we'll just leave it like that. I was going to say we can think of 4 as 2 squared, and you can bring a factor of 2 out front, but yeah, you don't have to. So that is our function value there. And then we said we are interested in what happens as x approaches 0. So our original function was 2x squared times natural log of the absolute value of x divided by 4. So that is a 0 times infinity, or 0 times negative infinity in determinate form. Now multiplying by that x squared is the same as dividing by 1 divided by x squared, because dividing by a fraction is the same as multiplying by the reciprocal. So these expressions are the same. Now the numerator is approaching negative infinity, because I've got a very large negative number here times 2. It's going to still go to negative infinity. And as x approaches 0, x squared is always positive. So this is 1 divided by a tiny positive number if x approaches 0 and x is not equal to 0, right? So 1 divided by a tiny positive number is a large positive number. So that's an infinity, negative infinity divided by infinity in determinate form. So we can use L'Hopital's rule. By L'Hopital's rule, we'll have the limit, this limit is equal to this limit. Take the derivative of the numerator. So you're going to have 2 times 1 divided by whatever was inside that function. So you've got the absolute value of x divided by 4. All divided by the derivative of x to the, or the derivative of 1 over x squared, which is the same as the derivative of x to the negative 2. I'm just going to do a little bit of algebra. So I have 2 times, multiply by the reciprocal, 4 divided by the absolute value of x. And then the derivative of x to the negative 2 can be found using the power rule. So we'll have negative 2 times x to the 1 less power. Negative 2 minus 1 is negative 3. So we're going to have 8 divided by the absolute value of x. And then this denominator is negative 2 divided by x cubed if I write that x to the negative 3 in the denominator there. Now I've got a fraction divided by a fraction. So we leave the fraction in the numerator alone, and then instead of dividing, we multiply and we flip this one. So we're gonna have a negative x cubed divided by 2 here. Now 2 goes into 8 4 times. Now I have the limit as x approaches 0. Of negative x cubed divided by the absolute value of x. You might say, well, when x is positive, we're going to have, this is just going to be negative x cubed divided by x. And when x is negative, the absolute value of x is negative x. And of course, it's 0 over 0 when x is 0, so that would be undefined in that case. But one of these x's will reduce here, and so we'll just have a negative x squared, and the limit of negative x squared as x approaches 0 is going to be 0. And then the negative and the negative reduce there, so we're going to have the limit as x approaches 0 of positive x squared, because one of the x's reduces. And so we get 0. So we get 0 either way, so the limit is 0. But the original function is undefined at 0. So that means that the graph of f has a removable discontinuity. That just means the limit exists. And the discontinuity is an x value. So it's removable discontinuities at x equals 0. And a hole in the graph, that open circle on the graph, at that x value, which is 0, and its limiting value, which in this case happens to be 0. It's a coincidence that we had a limiting value of 0 in a different function or another function as well. So we know now this function has a hole in it at 0. And we know that at the critical points, the y values are equal to 32 divided by e times this quantity, natural log of 4 minus 1/2. And I'm not sure what that is approximately. Okay, so the critical points are at x equals negative 4 divided by the square root of e and positive 4 divided by the square root of e. We get the same y value there. Okay. And f prime, we can determine the sign of f prime using a sign chart. We want to list the critical numbers on the sign chart. So we've got negative 4 divided by square root of e, 0, and positive 4 divided by square root of e. And f prime was 2x times 2 natural log of the absolute value of x divided by 4 plus 1. Now 2x is negative when x is negative, and positive when x is positive. And then this changes signs at x equals plus or minus 4 divided by the square root of e. So you might say, okay, well, when is it positive and when is it negative? Well, let's look at this graph. If there wasn't an absolute value there, I would just say that the domain would be 0 to infinity, and natural log of 1 is 0. So when I have x equals 4 here, I'd have a natural log of 1, which is 0 when x equals 4. So if I take that graph and I multiply all the y values by 2, and then I shift the whole graph up 1 unit, when x equals 4, we get 2 times natural log of 1, which is 0, plus 1. So 2 times 0 is 0 plus 1, which is 1. It's going to look like that. And then the graph is roughly going to have that shape. That's y equals 2 times the natural log of the absolute, or of just x divided by 4 plus 1. Now, because this function has an absolute value in it, it's going to look the same on the other side. At -4, we're going to have a y value of 1. And it's going to look like that. You say, okay, now where is this function positive versus where is it negative? Well, we can see it's positive from here until we get to that x value. And I claim that that x value is -4 divided by the square root of e. So it's going to be positive on this branch. And then it's negative from that x-intercept to 0. And then we see the y values are negative here. And I claim that that x-intercept is 4 divided by square root of e. And then it's positive over here. And I'm claiming that because we found those by setting this expression equal to 0. We said that that function is equal to 0 when x equals plus or minus 4 divided by square root of e. So that means this graph must have zeros at x equals plus or minus 4 divided by square root of e. So we have positive values, negative values, and positive values. So I'm going to write positive, negative, negative, positive there. So f prime is a positive, or negative times a positive, which is negative. Then it's a negative times a negative, which is positive. Then it's a positive times a negative, which is negative. And then a positive times a positive, which is positive. So this tells me that the function, the sign of being negative tells me that f prime is negative. So the original function f must be decreasing. And then this was a 0 of the derivative. So the function goes from decreasing to having a 0 slope to increasing. So we're going to have a relative minimum there. And then at positive 4 divided by square root of e, the function goes from decreasing to having a 0 slope to increasing. Now here, we do have a well-defined limit, but the function value does not exist. So the function is going to go from increasing to not having any derivative because the function is discontinuous there, to decreasing. So this would have been a relative max, but we don't actually get the relative max because the function isn't defined at 0. So from this sign chart, we can see that we have relative mins at plus or minus 4 divided by square root of e. And those minimum values are equal to this expression. I'm not sure what that is. And then we would have had a maximum here at 0, but yeah, the function's undefined there. So we do not have a maximum at 0. Okay. So by the first derivative test, these are relative mins. Okay. And we know where the function is decreasing, increasing, decreasing, and increasing. We could just read those intervals. So it's increasing on the interval from -4 divided by the square root of e to 0, and 4 divided by the square root of e to infinity. And it's decreasing on -infinity to -4 divided by the square root of e, and 0 to 4, or 0 to 4 divided by the positive square root of e. All right. So it's decreasing, then increasing, then decreasing, then increasing. And then we also want to know about concavity. So let's compute the second derivative. That was our first derivative. So we can compute the second derivative as well by taking the derivative of the first derivative. Now this is a product, so we're going to use the product rule when we take the derivative. So the derivative of a product is the derivative of the first times the second. So we're going to have 4. The derivative of 4x is 4 times the second function. Then we'll add the derivative of the second, which is 1 divided by that inside function. And actually, we don't need the absolute value bars there. Times the derivative of the inside. Well, the derivative of x over 4 is just 1/4 because it's the same as 1/4 x, right? That's the derivative of the second. Don't forget to multiply by the first. The 4 is reduced there. And that's a 4x divided by 1. The x is reduced there. So that's the derivative of this product. And then we add the derivative of 2x, which is just a 2. So we end up with 4 natural log of the absolute value of x divided by 4. And then we get a 1 times 1 times 4 here, plus 2. When we simplify that, we end up with 4 times the natural log of the absolute value of x divided by 4, plus 6. Okay, so that is our second derivative. The x values that cause that to be 0 are potential points of inflection. If the second derivative changes signs at those x values, then those are the x coordinates of points of inflection. So we'll find the x values that cause this to be 0 by solving for the natural log of x first. So we're going to have natural log of the absolute value of x over 4 equals, subtract the 6 from both sides, divide by 4. The 2's will reduce. And then to get rid of that logarithm, we'll exponentiate on both sides. So I have the absolute value of x divided by 4 equals this e to the negative 3/2 power, or 1 divided by the square root of e cubed. If we multiply both sides by 4, and then say the absolute value of x equals that positive number, has the solution set plus or minus that positive number, then we've found 2 zeros of that second derivative. So the second derivative is 0 at x equals a positive 4 divided by the square root of e cubed, which you can rewrite if you want to as e times the square root of e, and negative 4 divided by the square root of e cubed. So let's make a sign chart. Or you can just write it as e to the 3/2 in that denominator, same thing. In order to find the sign of that, we'll look at the graph of 4 times natural log of the absolute value of x over 4 plus 6. So that function has a vertical asymptote at x equals 0. Then when x equals 4, we're going to have natural log of 1, which is 0. So we'll have 4 times 0, which is 0, plus 6. So we get 6. And then it's just going to look like a logarithm. And we're going to have symmetry. So it's going to look the same on the other side. And then it will cross the x-axis at 2 values. I claim those 2 values are negative 4 divided by e to the 3/2 and positive 4 divided by e to the 3/2. Just from this graph of the second derivative, we can, and this is y double prime equals 4 times the natural log of the absolute value of x over 4 plus 6. We can see the y values are positive from on this interval and this interval. So our second derivative is positive here and here. And then the second derivative is negative in between those two. And we skip 0 because x equals 0 is not in the domain of that. So the second derivative is negative on this interval from that value to 0, and negative on that interval. Okay, so now we know where our graph is concave upward and concave downward. So the original function f is concave upward when the second derivative is positive. So it's going to be concave upward on negative infinity to -4 divided by e to the 3/2, and +4 divided by e to the 3/2 to infinity. And then it's concave downward on this interval and this interval. So from -4 over e to the 3/2 to 0, and 0 to +4 over e to the 3/2 as well. Okay. So we know where the graph is concave upward, we know where it's concave downward, we know where we don't have a vertical asymptote on the original function, although we do have a vertical asymptote on the second derivative. We've got a removable discontinuity at 0. But with these pieces of information, we can graph the function. We've got where it's increasing, where it's decreasing, where it's concave upward, and where it's concave downward. So let's plot those points on Desmos and then look at the graph and verify that the graph is what it's supposed to be. Okay, so this is our graph. And this is f prime. F prime was equal to 0 at x equals ±4 divided by the square root of e. So let's evaluate f at 4 divided by the square root of e and see what those y values look like. So our y value is approximately -5.886. And we'll substitute the negative x value as well. We get the same y value over there on the other side. Now the exact value was, if I did the calculations correctly, 32 divided by e times natural log of 4 minus 1/2. And I didn't get that calculation right. I had ±4 divided by the square root of e is 16 divided by e. So I had 2 times 16 over e was 32 over e. So I was evaluating this function there. And then we had this expression evaluated at 4 divided by square root of e. I forgot to divide them by 4. Okay. So this should actually be 1 divided by the square root of e. Because if I divided those numerators by 4. So then I'd have natural log of 1 here, which is 0. Yep, and that's the correct y value. All right. So I made I forgot to divide by 4 because it was supposed to be 1/4 of x, not just x inside the absolute value bars. When I actually divided by the 4, I got the right answer. Okay, so that is the same. This exact answer is the same. And actually, it would be, I'd simplify it to -16 divided by e. All right, so those are our values. And then we also said, let's look at the functions look at the function at the points of inflection. That second derivative changes signs at plus and minus 4 over e to the 3/2. So is that a point of inflection? Did I account for the 4 this time? I did. Okay, I think that's correct. So that is one point of inflection. We're going to see something similar on the other side. So there's some symmetry again. So the graph looks like it's concave upward or concave downward here, concave downward on this interval, concave downward on this interval. And then it's supposed to be concave upward on this interval and concave upward on that interval. I think that's consistent with what the graph looks like. I'm still using multiples of pi over 4 here. Let's just use 1. And maybe we should try that zoom square thing to make the dimensions a little bit better. Oh, it doesn't give us the option this time. All right. So I think we see everything that we're supposed to see. The first derivative sign chart said our function goes from decreasing to having a 0 slope to increasing, and then decreasing, and then increasing again. And that's what we have here. We have relative mins at these two x values, which were plus and minus 4 divided by the square root of 8. And then we would have had a max at 0, but the function was undefined at 0. So we just have a removable discontinuity there. The function changes from concave upward to concave downward at these 2 points. So those are points of inflection. Now, if we want, we can also graph the first derivative and second derivative on the same screen. It's actually easier if we don't label all the points because they can be a little bit distracting. Actually, I want to label the minimum values. Maybe we'll plot the points of inflection, but not label them. Okay. So let's look at the first derivative. The first derivative looks like this. So that's kind of cool. We see that the first derivative is 0 at that x value, that negative 2.4612, which is when the function has a relative minimum. And we see that the first derivative is also 0 at x equals 0. Well, actually, it's not actually going to be 0 there because the natural log is not defined at x equals 0. So this is actually going to have a removable discontinuity at x equals 0 as well. But the function goes from negative to 0 to positive at this x value. So the original function should go from decreasing to having a 0 slope to increasing, and it does. And then at this x value, the function goes from having a positive slope to a 0 slope to a negative slope, positive derivative to a 0 derivative to a negative derivative. So I would expect the function to be increasing to going to 0 and then decreasing. But again, 0 is not on any of these graphs. So there's actually an open circle there. So we don't have a relative max, but we would have if we removed that discontinuity by redefining the function at x equals 0 to be its limit of 0. And then this function has a relative min at this x value because the derivative goes from negative to 0 to positive at that x value. So our original function goes from decreasing to having a 0 slope to increasing at that x value. And then if we look at the second derivative, we see that the second derivative is positive until we get to this x value. And that 0 of the second derivative is equal to, or the x coordinate of the 0 of the second derivative is equal to the x coordinate of our point of inflection. So the function, the second derivative is positive here. That's when the graph is concave upward. And then from here to 0, the second derivative is negative. So the graph is concave downward. And then we have symmetry with concave downward on this side and then concave upward over here, which is consistent with the y values on the graph of f double prime. And we can compare f double prime and f prime if we want to. We see that when f double prime has a 0, that f prime has a maximum because f double prime is going from positive to 0 to negative. So f prime is going from increasing to having a 0 slope to decreasing. And at the other 0 of f double prime, the f double prime is going from negative to 0 to positive, and the original function's derivative is going from, well, the slope is going from, or yes, the function's going from decreasing to having a 0 slope to increasing at that point. So this orange graph is the slope of this orange graph is the second derivative and the teal graph is the first derivative. So the orange graph should be the slope of the first, the teal graph should be, or the orange graph should be the slope of the teal graph. That's what I meant to say. And it is. So we can put all those pieces together and then graph them, and we see that everything is as it should be. We've got minimums there. We would have had a maximum there. We've got points of inflection there and there. So that is our function. All right. And we've got that. I think that's cool that we've got the removable discontinuity at x equals 0 as well. All right. So that's that. We know when the graph is concave upward, concave downward, increasing and decreasing. We wrote that all in the paper. We evaluated the function at the relative extrema. We evaluated the function, or at the x coordinates of the relative extrema. We evaluated that limit as x approaches 0 from the left and the right. And we found the function values at the inflection points as well. Not on paper, but using Desmos, we found them to be these two values. So I think we did it. I think we graphed f, and we're able to analyze it using its first and second derivative and limits as well.